unit step function. So don't read too much into the step function. Okay? So you got to remember it's either 1 or 0. It's a very, very simple function. Some people try to read into it too much, but don't. So if I have a unit step function, they typically define it with the symbol of ut. Actually, I should subtract the number from it. So we typically are talking about some time, relative to some time. Now, t naught could be 0, but what this function is here, it's either 0 or 1. And what it does here is it really replaces a switch. So if t is less than t naught, this is telling me the turn on time. So then if I'm at t greater than or equal to t naught, then it's on. And so if I was to sort of like graph this thing, this function literally looks like this here. It's a 0, it's always 0, and then as soon as you get to t naught, it then jumps up. Where this value here is just 1. So it's either 0 or that. And the reason why this is useful here is that this then becomes, you can actually have sources that turn on or off here. And so what we find here is that we use step functions to turn on or off sources. And one very simple circuit that will show you what do I mean by a switch here is that imagine that I have a voltage source like this. And what you're going to see here is that I have a combination of switches. Now, the way I'm setting this up here with these switches is not a very good switch here because it would be opening or shorting the voltage depending on how you want to look at it. But you can see here is that if this is my switch here, and what I'm looking at here is that I'm looking at this guy right here. So I want to know what the voltage is at this point. So I'm going to say that this is plus or minus. And I'm looking, what is the drop across this open right here? And now I can combine this circuit. I mean, I can attach the circuit to this voltage source here. But when this switch is at this one position, let's call this 1. So at position 1, we see that we have literally an open with no voltage source. But if I now take that switch here and I close that switch so that I move it into position 2 here, we now see that the position 2 tells me that the open has voltage Vs. So it's either off or on, if I could say it that way. So then, instead of drawing this circuit, I could redraw the circuit so that I write this as Vs of u of t minus 0, like this. So at anything less than 0, the source isn't on. Anything greater than 0, I now have a voltage source that's turned on, and then it now participates in the rest of the circuit here. And that's really the only reason that we want to use that, right? Just to simplify what's going on. Okay, so now I want to get into time-dependent circuits. Here we go. You guys ready? steps here. You wanna, how do we say it in ordinary language? Brace yourself. Okay, there we go. So now we want to look at the response of first order circuits to time dependent sources. Now, let's just be real clear here. What we've been doing up to this point has been what? Constant sources. You can't apply a constant source solution to a time-dependent solution. Okay? All you got to do is look at the source. If it's a constant value, then you do the other one. But if it's a time-dependent, you can't use that other stuff. Some of you SOBs are going to try to use the constant value for the time-dependent source. I'm going like, you can't do that, homie. Right? You can't do that. It's a different process altogether here. So, what's the difference between these two? So if I have a constant source input, we saw that we had an equation that read like this. For this k, we define that to be a constant. When we have a time-dependent input, what you're going to find here is that you're going to get a very similar form. But now we have a function of time. This is a function of time. You cannot ignore the function of time. And so what you're going to find here is that because that's a function of time, we have to use new techniques in order to solve this thing. Now, could we go in and calculate a Thevenin circuit? The answer is yes. Can we go in and calculate a Norton circuit? The answer is yes. But it turns out that it becomes more time efficient to derive the first order equation constantly. And the reason why is here is that one of the solutions, the forced response of the circuit, changes. The natural response of the circuit doesn't change, but the forced response changes. And it's typically more time efficient to just start doing this. So when you were taking your differential equations class here, and when you were looking at your solutions, you had a homogeneous solution, which you probably got pretty quick. So were we. But then the particular solution was more time consuming. And that's where we're at here. And going back the other way, it turns out that you're making multiple steps, and then you still got to get the particular solution. So it's not as efficient. So what we're going to find here is that there's going to be two significant changes from constant source solutions. Okay. So the first thing that you're going to find here is that, one, I'm going to repeat here, the solution for RC, RL, constant source, are not valid. So that means I can't come in here and use this guy here. I cannot use this solution. Okay? This is not valid anymore. So what you're going to find here is that we're going to have to derive the solution every single time. And what you're going to see here is that you're going to see something like this here. That when I look at my solution for a time dependent, you're going to have what we call a natural response. And in the language of circuits, you're going to have a forced response. Right? So this is the homogeneous solution. And this guy here is the particular solution. So this will come very quick, as we'll find out. We almost get it from this guy right here. And then this is what we got to really pay attention to. So this is not valid. This is what we got to do. So what you're going to find here, let's see, how much space do we need? Actually, I'm going to go the other way. Actually, I want to shine something on the board here. So I'm going to erase this right there. So right there. Okay? Because I want that space empty. Okay, so that solution's not valid. This solution is valid. And what you're going to find here is that the next thing that we want to look at here is that what we're going to see here is that the forced response should look like the effective source. The forced response should look exactly like the effective source. So what do I mean by this? What I mean by this here is that our effective source is either going to look something like this. It's either going to be K1 plus K2 e to the minus omega t, or AT. Maybe I call it AT. Or it's going to look K1 plus K2 sine omega t, K3 cosine omega t. So it's got to look either form like this here. So let's think about this here for a moment here. What do I mean by this term here? What I mean by this is, imagine that I have a circuit that has a voltage source that looks something like this. So I have some circuit here, and here's the capacitor. So that just means that there's something in there. I don't know what it is. But what I want you to think about is that I want you to look at this source. This source is sinusoidal. If it's sinusoidal, what's it going to do to this cap? That source is going to drive that cap so that it's behaving in exactly the same way. It's going to be doing this, right? It's going to be taking charge on, off, on, off. And as it's doing that, we would expect then that the voltage of the cap to look like the source. But according to differential equations, I can't write a source like this. I need to essentially span the solution space in terms of orthogonal polynomials. So I would expect then that the source should be proportional to maybe something like b1 sine omega t plus b2 cosine omega t. That's what I mean by it behaving exactly like the source. The same thing happens with an exponential source. What do exponential sources do? What they typically do here is that they give it what? A burst of energy for a very brief amount of time. So, but as over time, what happens to that exponential? It decays. So that decaying term right there does what? It gives it a boost, and then it suddenly dies down. So what would I expect to the voltage of a cap if it was doing to that? Well, it's going to see a boost at some point, and then over time it goes back to maybe its original value. So anytime I look at that force response, looking at what's on the right side of the equation, right, this term right here tells me that that's exactly the way the solution should behave, the cap or the inductor. It doesn't matter which one we're going to be looking at here. So let's see if I could sort of like word this thing, and then I'm going to write this down. I'm actually not going to write it down. I'm going to show you online where the process is. Okay, so what we're going to do here is that we're going to use simple circuits to calculate the first order equation for a circuit. What does that mean? If I have a capacitor, I'm going to have to connect two variables. I'm going to use either KVL or KCL to connect the current and the voltage of the capacitor, or the current and the voltage of the inductor. So I'm either using KCL, KVL, or a combination of the two. Once I have that, I'm going to have a first order equation. So when I have that first order equation, I'm going to have two solutions: a natural response, a homogeneous solution, a force response, a particular solution. When you look at that force response, depending on the circuit, you could have two constants, maybe even three constants. We use the forced, to get the force response, those three constants, we typically use our equation for the first order equation to get those constants. You're going to see that I'm going to use the same constants every single time. I'm going to call them B1, B2, B3. Those B's are always associated with the force response. Once I get those, then my whole job, right? First order differential equation has that what? One constant. What's that one constant? It's the initial voltage of the capacitor. It's the initial current of the inductor. Once I get that, then what ends up happening is that I now impose that initial condition on the capacitor and the inductor, and I solve for the solution for the constant A. A is associated with the natural response. But I got to get the force response completely before I can touch the natural response. And that's a big, error in calculating these problems. You got to remember that. Okay, you got to remember that. Now, let me go show you where this is at. So if I come in here, what I want to do here is I want to take you to the web page, and if you look at the web page, look at this: first order time dependent. Okay? So if I click on this, okay, these are some of the solving strategies that I'm recommending here. So the first thing, you got to have these memorized. There's people by exam 2 comes, and people say like, why didn't you write these on here? Dude, if you don't got it memorized by then, it doesn't matter. Okay? You got to know these things, right? You got to know these things. Because you should have been using the hell out of these in Chapter 8. So here we go. You got to derive the first order equation. How do I derive this? I've got to write one equation that contains the voltage of the cap or the current of the inductor. You got to do where I connect both of these. And then, or if I have an inductor circuit, I got to connect the current of the inductor or the voltage. Is this too yellow or is this just green? I don't know if this is any better. Okay? Then what we're going to do here is that we're going to rewrite it so that it comes into this natural form, this normal form. Why do we want it that way? It turns out that if you write it this way, no constant term here, we can pick off that time constant for the circuit. That's why we want to do that. So once I have this solution here, then there's this sort of like process. I'm hoping to use the word rhythm, sort of like get into the rhythm of this process. Don't try to memorize steps. So sort of like get into this rhythm of how you move from one step to the next. So then what do? Then I know the solution to this. Why? Because this term right here is going to tell me what the solution form is. So I'm going to get a natural and a forced response. My natural response looks like this, just like in the previous, like in the beginning of this chapter. And then I get possibly 3 terms for the forced response. So this forced response, I know. Why do I know that? I know that because we're only going to deal with 2 types of forced response. Either exponential or sine or cosine. So if I have an exponential response like that, then I got to have this right here. It has to be the same form. If I have this form, it's got to be that form. So then what's my number 1 job? Once I write the whole solution here, then my job here is to find B1, B2, B3. So how do I get my B's? I take this solution and I plug it into the differential equation. And when I plug it in, this should then be able to have me solve for all of the B constants. If you're not solving for all of the B constants, you miss something. You got to go back. And then I go get the natural response. How do I get the natural response? I pick off the tau from the equation, and then I write the A. So I got my time, and then I got the A here. So then, when I look at the whole solution, A is unknown, B1, B2, B3 are known. So as a consequence, I then look at the initial condition. By looking at the initial condition, I set this thing t equal to 0, and then these terms will typically drop out. Either the sine goes to 0, or the cosine goes to 1. Or if I have exponential terms, the exponential at 0 should be 1. So all the time dependence cancels out. So then, that allows me to solve for the constant A. So I get A, so now I have my full solution. I have numbers in all of these equations, either this equation here, and so now what do? I got to go solve the circuit problem. So what I want to do here is I want to go through an example. This example is long, okay? Obviously, we're not going to finish it. We're probably right at the end of class. But I'm going to use this process here. I'm not going to write it down, but you're going to see me use this process in detail. So we will not be doing anything. Right? It doesn't make any sense. I'll see you on Friday or Monday. So remember, I'm going to tell you, you got a tall order. On Monday, for those time-dependent circuits, that should be all that should be left on your homework. Okay? You should solve everything but the time-dependent circuits. So when it comes to Monday afternoon and Tuesday, you're working on those circuits. Remember, be effective with your time.